In this video, we're going to investigate quadratic functions and their properties. So we'll be looking at parabolas, which are the shape of the quadratic function graphs. We'll be um, creating the graphs, finding the vertex, the high or low point, the axis of symmetry, and finding the maximum or minimum values, which will be connected to the vertices. So we'll start with a definition. A quadratic function is any function of this form where f of x is a constant times x squared plus a constant times x plus another constant, where the only requirement on the coefficient a, b, and c is that a is not 0. So there has to be an x squared term involved. There need not be an x term or a constant. There can be up to terms, but there has to be an x squared, and there can't be any higher degree term. So let's take a look at graphing this first quadratic function. F of x equals 3x squared plus 12x plus 5. So in the notation of the previous definition, a would be 3, b is 12, c is 5. One way we can graph these quadratic functions is by what's called completing the square and then using transformations. So let's go through the process for completing the square. Our goal is to try to get to this form, f of x equals a x minus h squared plus k. That's our goal. The a value here is always going to be the same as the a from the function that's given. So what we've got right now is f of x is 3x squared plus 12x plus 5. What we need to do is factor the 3 off of the x squared. And when we do that, we're also going to factor it out of the linear term. So in this case, out of the 12x. But we're going to leave the 5 off by itself. So what we did is factor the 3 out of the first two terms, the x squared and the x terms, but leave the 5 out there on its own. So we're just rewriting this function. So we can factor that 3 out, that's fine. Notice I left it blank because what I want to do is now look at this group, the x squared plus 4x, and I want to make it a perfect square binomial so that in the next line I can rewrite it as a group squared instead of x squared plus 4x plus something else. So this is the key. I want to add something here, and the way I decide what to add there is I look at what's called the b coefficient on this group, so the linear coefficient. So b, I cut it in half and I square it. So I'm ignoring the 3, I'm not looking back to the 12, I'm only looking at this 4 that's here now that I've factored the 3 out. So I take 4, I cut it in half and I square it, and that gives me 4 again, so I add 4 to the group. So it's not that I always add the same thing as this b. I always cut this in half and square it. This just so happens to be actually 4 again. But now, notice that what I really did here was I have this 3 times this 4. So when I wrote a plus 4, I really did plus 12. So I need to undo that over here to keep everything the same. So I'm going to subtract 12, which is coming from, I really added 12 when I wrote this plus 4 because it's multiplied by 3. So now I need to subtract 12 on this other side. And then I'm going to rewrite this group as x plus 2 squared, because x plus 2 squared is x squared plus 4x plus 4. Keep the 3 on the outside, ignore that when you're doing the rewriting the trinomial as a binomial squared. And now combine these terms. I have a 5 minus 12, so that's a minus 7. So my function is actually 3 times x plus 2 squared minus 7. So the shape of this graph is like y equals x squared, but I have some transformations. I have a 3 times everything, so I have a vertical stretch by a factor of 3. I have a left 2 shift from the x plus 2 inside the square. And I have a down 7 shift. From the minus 7 outside. Right? So I can track the key points from x squared. Let's track 0, 0, 1, 1, 2, 4, negative 1, 1, and negative 2, 4, and apply these transformations. The shifts are always last. Vertical stretch by a factor of 3 is going to multiply all the y coordinates by 3. So this would go to 0, 0, 1, 3, 2, 12, negative 1, 3, and negative 2, 12. Left 2, that's going to subtract 2 from all the x's. 0, 12, negative 3, 12, and negative 4, 12. Then down 7, kind of running out of room here, we'll have negative 2, negative 7, negative 1, negative 4, 0, 5, negative 3, 5, and negative 4. Something's not right here. Let's see, this should have been negative 3, 3 at the last line. Sorry about that. Negative 3, 3 when I go down 7 is going to be negative 3, negative 4. Negative 4, 12 when I move down 7 will be negative 4, 5. So these would be my final points. So negative 2, negative 7, negative 1, negative 4, 0, 5, negative 3, negative 4, and negative 4, 5. So we have a parabola opening upward, which, if you remember, is determined by the sign of A. If A is positive, it opens upward. If A is negative, it opens downward. We can write that up here. So if A is greater than 0, we'll have this shape. If A is less than 0, we'll have this shape. And we used the general shape of x squared and then took those key points and applied the transformations to them to get the new function. So that's one way to get to the graph of a quadratic function. We will also look at how to get to the graph without completing the square, just using what's called the vertex formula. Before we move on from that, let's talk about the domain, the range, intervals of increase, intervals of decrease, things like that. So for this particular function, I can see the domain is all reals because it extends left and right without bound. The range is not all reals, right? There is a low point here. The low point appears to be, what did we have? Negative 2, negative 7. So the range would be that low point, negative 7, up to infinity. The vertex of that graph is the place where there's that low point, negative 2, negative 7. We have an interval of decrease from negative infinity to negative 2. We have an interval of increase from x equals -2 to infinity. Remember, those are x intervals. So the graph is falling to the left of -2 and rising to the right of -2. And we have a relative min of -7. It occurs at x equals -2. We could also talk about the x and y intercepts for this function. We'll talk about that more when we get to the next page here. So if we want to find the vertex for a quadratic function without going through that completing the square process, we can use this vertex formula that says if we have the function in this form, ax squared plus bx plus c, where a isn't 0, then what we can do is find the vertex using this formula. Take the opposite of b, divide it by 2a, and that's the x coordinate. And once you've found that, just plug the x coordinate into the function to find the y. So it's not like you need to memorize the pattern for the y, you just find the x using the pattern, then take the x, put it into the function, and get the y that way. The axis of symmetry, that's the line that cuts through the middle of the graph. That'll be a vertical line, so it's an x equals, and it's always passing through the vertex, so x equals the same as the x coordinate of the vertex. And then we will also talk about finding the x-intercept, so the places the graph crosses the x-axis. And remember, you always, no matter what kind of function you have, you always want to set the function, the y values, to 0 to get the x-intercepts. So you would be solving ax squared plus bx plus c equals 0. And you can always factor that, try to factor, and if that's not working, use the quadratic formula. So the quadratic formula is here, you need to memorize that. And that applies when you have a quadratic function in this form equal to 0. If there are 2 answers, you get 2 x-intercepts. If there's 1 answer, you get 1 x-intercept. And if you only have complex answers, then you get no x-intercepts. The number of answers you have is going to be tied to this quantity in here, just the b squared minus 4ac. So sometimes it's worth taking the time to just check that quantity to know whether there are going to be any x-intercepts or not. If you find that b squared minus 4ac is negative, then you don't need to go through the whole calculation. You can say, wait, since that's negative, I have a negative inside the square root, and there won't be any x-intercepts. So you can avoid the whole formula just by noticing that b squared minus 4ac is negative. If b squared minus 4ac is positive or 0, then you still need to go through the work of the whole formula to get the x-intercepts. But if it's negative, you can save yourself some time by catching it early. So let's go through a bunch of examples. Find the vertex, axis of symmetry, and intercepts of this graph. Let's also add intervals of increase and decrease to that list. So we're not going to actually sketch this graph necessarily very carefully, but we're going to find all the details just analytically. So the vertex, we're thinking, all right, so since A is positive, we know this graph opens upward. So this vertex is a low point. Right? It's a relative minimum because it's lower than all the other points around it. The x-coordinate is, we can just do opposite of b over 2a, which in this case is the opposite of -1 over 2 times 2, so a fourth. And the y-coordinate of the vertex then is f of a fourth. This is going to be a little bit ugly, so 2 times a fourth squared minus a fourth plus 2. 1/4 squared is 1/16, so we'd have 2 times 1/16, or 2/16, minus a fourth plus 2. 1/8 minus a fourth plus 2. We could get a common denominator of 8. 1 over 8 minus, this would be 2 over 8, multiply by 2 over 2. And 2 is 16 over 8. So it looks like we have 17 minus 2, so 15 over 8, which is the same thing as 1 7/8. It's a lot of work to get the vertex, but the vertex is 1/4 for the x, and then 15/8 or 1 7/8 for the y. Knowing that vertex, we can now list, well, the domain we can find without the vertex. It's always going to be all real numbers because we don't have any problems with any of the x's. We don't have any denominators. We don't have any radicals of even index. So the domain for any quadratic function is all real numbers, but the range depends on the vertex. The range is going to be from this low y value, which is 1 7/8, to infinity. Because we knew that the graph opened upward, we know that y-coordinate is the lowest y-coordinate. At this point, we can also determine the intervals of increase and decrease. We have decrease from left of 1/4 up to 1/4, so negative infinity to 1/4. We always list that as an open interval. Interval of increase would be from that point x equals a fourth to infinity, to the right of there. We can also list the axis of symmetry. Remember, that's the vertical line that goes through the vertex. So the axis of symmetry should be x equals a fourth. You don't want to write just a fourth because that's a number, not a line. For it to be the equation of a line, it needs to be x equals a fourth to say it's that vertical line through 1/4. We still need the intercepts, but everything else we were able to get just based on the vertex. So the x-intercepts, we set the function value equal to 0 and solve for x. We could try to factor that. I'm going to just use the quadratic formula. So we have, in this case, 1 plus or minus b squared would be negative 1 squared, so 1 minus 4 times 2 times 2. Notice that's negative 1 minus 16, so negative 15 inside there. Because of that, we know there are no x-intercepts. Because what we're getting are complex solutions to this equation. The y-intercept, we just plug in f of 0, so 0 for x. We get 0 minus 0 plus 2. So 0, 2 for the y-intercept. One other note here, if we had been thinking about the vertex and the graph, we found that the vertex was 1/4, 1 7/8. So over here in quadrant 1, and we knew the graph opened upward. So just based on the graph, we could have concluded that there were no x-intercepts. We went through the analytical argument as well, but we didn't need that. That's just kind of extra. So everything fits together. The graph is opening upward and the vertex is above the x-axis, so there shouldn't be any x-intercepts. And we found that when we tried to solve that function equal to 0, we found that there weren't any real solutions. So everything fits together. So this is not an accurate and detailed graph. If you were asked to graph this, I would want more details than that, but at least it's a rough sketch that tells us, wait a second, yeah, there aren't going to be any x-intercepts. Alright, so let's do all the details for these two graphs. Find the vertex, axis of symmetry, intercepts, sketch the graph, list the domain and range. Let's also add again and intervals of increase and decrease. So I chose these two because they are in different forms. The first one is in the form where we can actually use the shifts and the transformations really easily. Right, so we can see this is a shape x squared reflected over the x-axis because the negative outside the function, stretched vertically by a factor of 2, and also shifted right 3 because that's inside the function, and up 2 because that's outside the function. The vertex is always going to follow the shifting. The stretch wouldn't change 0, 0, so the vertex will follow the shifting. So we know the vertex of this is going to be 3 to the right and 2 up from where 0, 0 was. We know it's going to open downward because of the negative 2. If we track 1, 1 and 2, 4, we can use symmetry to find the images of negative 1, 1 and negative 2, 4. So let's track these two. If we reflect over the x-axis, the y-coordinates become opposite. We stretch vertically by a factor of 2, the y's get doubled. If we shift right 3, the x's go up 3. And finally, if we go up 2, the y's are increased by 2. So we have 4, 0, and 5, negative 6. And then we can use symmetry on the other side. We'd have 2, 0, and 1, negative 6 also. So we've already got a good picture of this thing. Just putting together the transformations with the shape of the y equals x squared and using its key points and transforming them. Let's see, what else do we want? So the vertex we can see from the shifting is going to be 3, 2, which means the range, since it's opening downward, is going to be negative infinity to 2. And we can say that we can see the x-intercepts from the graph happen to be 2, 0, and 4, 0. We'll go look at how we could find those another way if we didn't have the graph already. The y-intercept. We want to calculate f of 0. In this form, that's not quite as easy as in the expanded form, but negative 2 times 0 minus 3 squared plus 2. We get negative 2 times negative 3 squared is 9 plus 2, so that would be, what, negative 16? So 0, negative 16. The axis of symmetry is going to go through the vertex. So that's going to be x equals 3, vertical line through 3. And what else did we need here? Domain, range, we have axis of symmetry, vertex, intercepts. Oh yes, intervals of increase and decrease. Remember, those are x intervals. The graph is first rising, so we'd say interval of increase would be negative infinity until we get to the x coordinate of the vertex, which is 3. Interval of decrease would be from the x coordinate of the vertex onward to the right, so 3 to infinity. Again, no mention of any y coordinates on the intervals of increase and decrease. Okay, so let's follow up here. We could see the x-intercepts from the graph, but just to demonstrate that if we were to try to find them algebraically, we'd get the same thing. So we set the function equal to 0, so we have 0 equals negative 2 x minus 3 squared plus 2. I wouldn't expand that. I would subtract 2, then divide by negative 2, so that's going to give me 1. Then take the positive or negative square root, so I'd have x minus 3 equals positive or negative square root of 1, which is just positive or negative 1. So x is either going to be 3 plus 1 or 3 minus 1. So we get 4 or 2. So we're going to get the same information whether we look at the graph or whether we go through it algebraically. If they come out even on the graph, that's fine, you can use those, but if this crosses in between some integers, then don't use your graph. Get the value using the algebra. We could also mention that there's a relative max of 2, happens to be at x equals 3, but the max value is 2. Okay, on to the next one. This one is not in the shifting and the transformation form, so we would use the vertex formula instead. So unless you really like to complete the square, there's not really a reason to do that. You can always use the vertex formula to get going on these if they're not in the nice shifted form already to begin with. So I would use the vertex formula to get the vertex, and I would usually start with that. So the vertex is going to be x coordinate opposite of b over 2a. Also notice in this example, a is 4, b is negative 8, and c is 0. There's not a constant term. So if one term is missing, you would have that coefficient being 0. Negative b, or the opposite of b over 2a, in this case would be 8 over 2 times 4, so 1. And then the y is just the function value evaluated at that x value. So f of 1, which is 4 minus 8, or negative 4. So we get 1, negative 4. So 1, negative 4 for the vertex. 1, 2, 3, 4. And we know this is opening upward. So already we can write down a lot of our information, right? So if that's the vertex and it's opening upward, we know the domain is always negative infinity to infinity. Using the vertex and the fact that this is opening upward, we can say the range is as low as negative 4 and then up from there. So negative 4 to infinity. Again, we're focusing on the y values for the range. The axis of symmetry that cuts the graph in half vertically needs to be a vertical line, so x equals, and you want the x coordinate of the vertex, so 1 in this case. We know the graph is decreasing at first, so we'd say interval of decrease from the left all the way to 1, so negative infinity till we get to x equals 1. And then the interval of increase, we want starting at x equals 1 and going to the right, so 1 to infinity. We can say there's a relative min at that vertex point. So the relative min is negative 4. It happens at x equals 1. And then from there we need to do some work, but all of that information we get from the vertex. So let's find the x-intercepts. We do that by setting the function equal to 0. And this one we can factor. We can factor a 4x out of this. So it looks like x equals 0 or x equals 2 are the x-intercepts. And since 0, 0 is an x-intercept, that's also the y-intercept. There. So now we can put the graph together. We've got enough information. Domain, range, intercepts, vertex, axis of symmetry, intervals of increase and decrease, relative min. I think that's everything. And a couple less standard examples. They're asking us here to determine the quadratic function whose graph is given. Things we can see from the graph. One important thing is that we can see what the vertex is. We can see that the vertex is 4, 2. We can see that it opens downward. So we know that A is negative. We can see another point on the graph is 2, negative 4. So let's think about this. We're trying to find the function. And for quadratic functions, we have two options. We can either work with a x minus h squared plus k and find a and h and k. Or we can work with f of x equals a x squared plus bx plus c and find a, b, and c. The nice thing here, we have two options. The nice thing here is that we can tell that we actually already are given h and k. So it's going to be easier for us to use this since h and k are given. So we're given h is 4 and k is 2 because we're given the vertex, right? So we know actually f of x is some constant that we don't know yet, x minus 4 squared plus 2. So what we can do is use the additional point to find a. So what we'll do is we'll fill in 2 for x and negative 4 for f of x, because when x is 2, the function value is negative 4. We don't know a, so we'll leave it like that. Fill in 2 for the x, and then we'll solve for a. So if I subtract 2, I have negative 6 equals a times negative 2 squared. That's just 4. So negative 6 equals 4a. So it looks like a is negative 6 over 4, or negative 3/2. So my answer is f of x equals, we figured out the coefficient that we need is negative 3/2, x minus 4 squared plus 2. Alright, so the next example, saying that the John Deere Company has found that the revenue in dollars from sales of heavy-duty tractors is a function of the unit price, P, in dollars that it charges. The revenue function here that's labeled R is given by R, revenue as a function of price, is negative 1/2 P squared plus 1900 P. They're asking what unit price should be charged to maximize revenue, and what's the maximum revenue. So we should be able to answer this without a calculator, just thinking carefully about this graph. The independent variable here is the price, and we want to fix the price so that the revenue, which is the dependent variable, is maximized. Right? So we want to figure out what's the price that's going to give us the maximum R value. The graph is a parabola, opening downward because the A coefficient is negative. So the graph has a maximum point, right? And the maximum point is the vertex of the parabola. So they're basically asking us, where's the vertex? But we need to make that connection. Right? They're asking us, what price should we charge to maximize the revenue? And what is that maximum revenue? So in other words, where's the vertex? That's the maximum point when the parabola is opening downward. So we can use our formula. P is what's normally in our x rule here. So P instead of x would be opposite of B over 2a. A is negative 1/2, B is 1900, and C is 0. So negative 1900 divided by 2 times negative 1/2 looks like negative 1900 divided by negative 1, so 1900. So the price would be 1900 at that high point, and the revenue at 1900 is going to be the maximum revenue. So negative 1/2 times 1900 squared plus 1900 times 1900. So that's the same as, this is 1900 squared, and that's negative a half 1900 squared. So that's the same as a half 1900 squared. So let's find that value. looks like $1,805,000. You can see when P is 0 that revenue is 0, which makes sense. If we don't charge anything, we're not going to make any money. So the graph is a parabola that looks like this, and we found this high point to have coordinates 1900, 1805000. So that's a picture of what's going on, and we should be able to generate that picture without a graphing calculator. And we can say then the maximum revenue is $1,805,000 if the unit price is 1900. And then a couple more less standard examples, just getting us to think about how the behavior of these quadratic functions. The first question is, can a quadratic function have a range of negative infinity to infinity? And if you think about the shape of a quadratic function, it either has to be opening upward or downward, but there's always a relative max or a relative min. So there's no way that the range can be negative infinity to infinity. So we'd say no. The graph is always a parabola with either a maximum y value or a minimum y value. So the range can't be all real numbers. And then the last question, what are the possibilities for the number of times the graphs of two different quadratic functions intersect? And we want to explain that. You can draw pictures to get started on this. Notice that it's actually different quadratic functions. So they can't be the same function. So we have two different quadratic functions. You can play around with pictures and come up with your guesses. And then to justify it, you would probably want to think about it this way. So if I have y equals a1x squared plus b1x plus c as one of my functions, c1, and the other is y equals a2x squared plus b2x plus c2, at an intersection point, I would have the first function equals the second function. Which is just a quadratic equation, right? So I'm going to have a1 minus a2 x squared plus b1 minus b2 x plus c1 minus c2 equals 0. So any quadratic equation can have either 1 or 2 or 0 solutions. So if there are 1 or 2 or 0 solutions to that equation, then there can be either 1 or 2 or 0 intersection points. Okay, so there's no way to get 3 intersection points or 4. There could be 2 or 1 or 0. So hopefully some of that is a review for you, but hopefully some of it is new too, especially these last couple of questions, thinking through Like what do these graphs have for restrictions of the ranges? Can it be everything or not? And how many times could they intersect?